Hello everybody. In this video, I'm going to go over some of the concepts in our first unit. The first thing I want to talk about is the difference between chemical properties and physical properties. Chemical properties are the properties that are affected by chemical reactions, and physical properties are the properties that are affected by physical changes. So, what are chemical reactions and what are physical changes? So, chemical reactions are the changes in matter that result in the reorganization of the atoms that comprise the initial matter or reactant. So we're going to have some sort of reorganization of chemical bonds. The way that the atoms that make up the matter are connected is going to be different before and after the chemical reaction. So after a chemical reaction, the reactant is transformed into a new form of matter, which we will call a product of the chemical reaction. And then physical changes are basically anything that isn't a chemical reaction. So physical changes are the changes in matter that don't result in a new form of matter. So let's look at some examples here. Examples of chemical reactions would be like burning. You start off with something like, say, a piece of wood. After you burned it, you see that it turns to ash and gases coming off of the flame. And it's very clear here that the matter that you're left with is very different than the matter that you started off with. Another example would be rusting. This is a process where you have metal and then it slowly turns into rust, the oxides of the metal that you started off with. An obvious one would be explosions. It's very obvious that there's been a big change there between the beginning material and the final material you have. And then more subtle ones, like say when you cut an apple and it turns brown. This is actually the same process of oxidation as rusting. You are having a chemical change in one of the components of the apple that is now making it brown. And then something that is kind of a classic one is like the science science class volcano or something, where you mix vinegar with baking soda. Vinegar is an acid, baking soda is a base. They react together to neutralize and release carbon dioxide, and you get this big fizzy kind of reaction happening. Physical changes are things like melting. Whether you have an ice cube or a glass of water, it's still water. It still has the same kind of properties. Boiling, exactly the same. Whether it's a liquid or a gas, it's still all connected the same way. No chemical reaction has happened. Heating up something, like heating up a piece of metal on the stove, like a skillet, for instance, you have not changed anything. You still wind up with the same skillet when you're done. And then something like maybe more exotic, like conducting. You can start passing electricity through a copper wire. You've changed something about the copper wire, but you haven't changed the wire itself. Once you turn the electricity off, it will still just remain copper wire. Various chemical properties are things like toxicity. It would be a chemical change for something to become more or less toxic to you. A compound is just going to have the toxicity that it has. Combustibility, so how well it burns. You would have to change something very fundamental about that matter in order to change how well it burns. And then something we're going to talk about a little bit later will be acidity and basicity. And these are intrinsic to a specific form of matter. You would have to have some sort of chemical reaction to change the acidity or basicity of a compound. Some example of physical properties are going to be things like melting point, so the temperature at which something melts; boiling point, the temperature at which something boils; the conductivity, how well it transfers electricity; ductility, This is how well it can be drawn out into like a wire, like copper is very ductile, and malleability, which is how well it can be stamped out into a thin sheet. So something like gold would be very malleable, and we make very thin sheets of gold in order to plate jewelry and things of that nature. So next I want to give you guys a little overview of the various fields of chemistry. And there are 5 major disciplines within chemistry. The first one I want to talk about is organic chemistry. And organic chemistry is really one of the oldest forms of chemistry. It kind of gets its own special place and its own discipline because we know so much about it because we've been studying it for so long. And basically, we started off by seeing that we were getting a lot of these different compounds from living things. So we were able to like extract or distill away all these different compounds from things that had once been alive. And that's where the word organic comes from, meaning life. And, but chemists now use this in a very specific way. We're not really talking about life here. Really what it is we're talking about the chemistry of matter that is made up of primarily carbon, because we are these carbon-based life forms. Carbon can form bonds with itself very readily. They are a special type of bond we call covalent bonds. We'll talk about that a little bit more. But typically we're really talking about the chemistry of carbon. And with that comes nitrogen, oxygen, sulfur, phosphorus, and the halogens. These are also going to be bound into various different organic compounds. But at the heart of it, in the backbone of it, you're always going to find your carbon there. If organic chemistry is the chemistry of carbon, inorganic chemistry is mostly just the chemistry of all of the other elements that we have and how they interact with one another. And in our world, it's becoming more and more pertinent that we learn a lot about this. You can think of like lithium batteries and the silicon that we use for computers and stuff. We're really learning a lot in the inorganic chemistry realm, and we're going to see a lot of benefit from that in the future. So what eventually happened is we started to realize that we really had missed something with organic chemistry, because as it turns out, once we take all these compounds outside of a living thing, they start to not behave the same way. You can't necessarily reproduce something that happens inside of a living thing on the bench top. And so we kind of spawned a whole new branch of chemistry that we call biochemistry. And this is really the chemistry of life. How do the reactions that are necessary to sustain life happen? And they often involve a lot of different organic compounds, but also we've discovered all new classifications of compounds and stuff from that, like lipids and hormones and proteins, DNA, RNA, all these different large macromolecules, big molecules that make life happen and make it necessary. And then we also started to discover that the real secret to making all these things happen are the catalysts that are there, the enzymes. Enzymes are allowing reactions to happen within living organisms that just aren't really reproducible on a benchtop without them. So that's a really exciting field of chemistry. The next field is going to be analytical chemistry, and this is pretty much exactly what you would think. It looks to answer the questions, what is something made of, and how much of this stuff is there really in it. So things like blood tests, for instance, that a doctor might send you to, they're using techniques in analytical chemistry to figure out what is in your blood and how much of it is there. They're checking the fluids. And you can see this also in things like water analysis and stuff, how much of different compounds are inside of the water, how much is safe to have in there. Analytical chemistry is probably really the largest field of chemistry in the sense that there's probably more analytical chemists working than any other out in industry because it's so useful and it's so essential to so many different things that we do. It's tough to think of a consumer product that would come to market without having to have some form of analytical chemist taking a look at it at some point. And then the last field of chemistry, the one that I studied the most in my graduate school, is physical chemistry. And this really investigates topics that are at the boundary between physics and chemistry. There's also another branch of called chemical physics, which is a little bit more on the physics side of it. But really, this is starting to ask those big questions like, what are atoms? What are they really made of? What are the rules around this? If we start to get smaller and smaller and looking at smaller and smaller, just a single atom or something like that, and it leads into things like quantum chemistry and quantum physics, where we find that the rules really don't hold up, and there's a lot of non-intuitive answers there. So the last thing I want to talk to you guys about is the scientific method. I think that this diagram really does a good job of explaining the scientific method, but there's a lot going on here. So I really want to just walk you guys through it a little bit here. And basically, the beginning of the scientific method is all about observation and curiosity. You saw something and you wanted to know how exactly does that work. And the very first thing that you're going to do is you're going to make like a little guess. You're going to say, I think this works this way. And the next thought you would have is, how can I be sure that it does or does not work that way? And you get into your experimental design phase and you design an experiment that is either going to confirm or deny your hypothesis here. That's going to say that your hypothesis is incorrect. So you perform the experiments and you make a bunch more observations. And two things are going to happen. Either you find, yes, my hypothesis was correct, or you find, no, my hypothesis isn't really correct, I got to tweak this a little bit. So if you find it's not true, you go right back to the first step. You go back and form a new hypothesis. You tweak your idea a little bit, and then you perform a new experiment, and you just keep going round and round until you get something that's consistent. Like, I now have a hypothesis, and I believe this is correct because I've done the experiment, and my data is suggesting that this is true. At that point, and this is probably the most important part of science, it's what really removes your bias from the thing, because you've convinced yourself at this point, but you need to know that it's really true. You need to know that that's not a mistake that you made. Your results are going to go out, and it's going to contribute to the body of knowledge. Okay, and what they mean by that is you're going to start showing other scientists, other really smart people who are working in this field, your results. You're going to go publish a paper, you're going to present this at a conference or something, and they're going to see it. And then they're going to go back through their own thought experiments. They're going to start doing this process in their own labs. They're going to be making hypotheses, and they're going to be looking at the experiments, and they're going to see, can I reproduce what you did? And if it turns out that they can't, then they're just going to kick that back to you. And they're going to say, we found that this really wasn't true. We think maybe it's just a little quirk of your setup or something. We can't reproduce this. You're going to have to go back to the drawing board on this and rework your hypothesis a little bit. But every once in a while, you shoot out your results, and it is true, right? You go back to your process here, and you go back and you publish another paper, and they say, you know what? We do see that this is true. We can reproduce this a lot, right? And basically what winds up happening is it now forks off into two paths, and this is where it's a little bit confusing. Okay? What they could say is that yes, the observations that you saw are happening, but your hypothesis doesn't really seem to hold up. We don't think that this hypothesis is quite correct, but it is happening. And in that case, it becomes what we call a law. So now we know that this is true, but we don't necessarily have a good idea about why it's true. We don't have our hypothesis. We don't know why it's happening, but we're sure that it is happening for the most part. We're going to call that a law. And then every once in a while, we'll say, oh, your observations are correct and your hypothesis holds up. Everything's seeming to line up here. And in that case, you wind up with a theory. And it would seem like a theory, just from the word, would be kind of lesser than a law, but it's not necessarily. A theory is true for the most part. We regularly see that it's true and that these observations are reproducible. And we feel like we have a good idea about what is causing that to happen. That our hypothesis is correct, and this is the reason it's happening, and this is what happens. And that's kind of the difference between a law and a theory.